All right. So you're going to tell me which of these four waves isn't like the others. We have microwaves, sound waves, light waves, and radio waves. And most of you are probably thinking to yourself, microwaves, that's different, because the other ones I can sense, the other one I use to heat up my food. Well, you'd be dead wrong. And why? The difference between them is sound waves, they require, it's basically vibrations of air or whatever material that event is occurring in. However, all three of the other kinds involve one single thing. They all are made of electromagnetic radiation, which we can call a photon. And what we're going to do in this unit is we're going to look at how those photons are either generated or interact with matter to gain a better understanding about the atom. So the two main properties we're going to look at for photons is one, the wavelength, and two, the frequency. We're going to see how that impacts different properties of it. Now, within the electromagnetic spectrum, we have a wide range of types of waves. The longest waves, which can be meters long, would be radio waves. They're relatively harmless. They're going through you all the time. And in fact, if you want to prove that to yourself, sit on your phone and see if you can receive a phone call. That would only happen if the radio waves are going to your antenna and getting right through you. Then we have microwaves, which are a little bit shorter than radio waves. And that's what we use to heat our food. You know, we blast our food with microwaves, and the water molecules in our food will actually start to rotate and have higher kinetic energy and raise the temperature. Then we have infrared waves, which are given off by warm objects. And then we finally get to the visible spectrum. And it's crazy to think that all of our ability to observe things has to do with light being either reflected or emitted by objects within a range from 700 nanometers in wavelength to 400 nanometers in wavelength. But just real quick, wavelength is the distance between two crests on adjacent waves. So the distance between the waves would be 700 nanometers. For red light, red, orange, yellow, green, blue, and violet. Who cares about indigo? And we get down to 400 nanometers for violet light. And outside of that range, we can't see. All of the visual information we gather just has to do with waves of those lengths hitting our eyes in a way that our brain can put it together, which is pretty crazy if you ask me. Then once you get past the visible spectrum, we get to the ultraviolet region. And also what we're going to notice, and we're going to get to this in the next thing, is as the wavelength gets shorter, going from visible on, we realize that those waves become more and more capable of causing damage. Like for visible light, you don't really need much protection. UV light, usually you wear sunblock. X-rays, you wear a lead vest, and gamma rays, you wear a bomb shelter. So let's take a look at some of these wave properties. This would be an example of a radio wave. Very long in wavelength. And if I pause it, the wavelength would be the distance between, or any two identical points on adjacent waves within the function would count. And you might be able to notice that the longer the wavelength, or the lower the frequency, which is how many cycles it goes through per second, the less energy it appears to have. So the higher the frequency, the more energy the waves would carry. So that's a direct relationship between frequency and energy, and it's an inverse relationship between wavelength and energy. Now, since all light and electromagnetic radiation travels at the same speed, the speed of light, which is 3.00 times 10 to the 8th meters per second, or 300 million meters per second, since it's traveling at the same speed, no matter what kind it is, the longer the wavelength is, the less cycles it's going to be going through. And the shorter the wavelength, the more times it's going to have to go up and down on its way traveling that same distance over that same period of time. So out of these, radio waves would have the least energy, gamma waves would have the highest energy, and out of the visible region, red light would have the least energy, and violet light would have the most. And we'll learn a little bit more about that when we look at the photoelectric effect in the next video. Now, the relationships we use for those, speed of light is equal to the wavelength times the frequency. And these are the symbols we use to represent that. This is called lambda, and this is called nu. So speed of light is equal to the wavelength, which we're going to measure in meters, times the frequency. And there's two main ways that's described. Hertz is the one that you hear most commonly, but it can also be written as inverse seconds. So the type of question I could ask you would be, to determine the wavelength of the radio waves emitted by 98.5, the Sports Hub, which I hope you all listened to on the way here. The frequency of that radiation is 98.5 megahertz, and as we've learned before that there are a million hertz and a megahertz. So what we would first have to do is just convert it, and we do that, and you get 9.85 times 10 to the 7th hertz, or inverse seconds. So if we're calculating the wavelength of that station, what we need to do is rearrange this equation to solve for wavelength. So we divide both sides by the frequency, and we end up with this. And we just divide the speed of light by the frequency, and we'd find that one of those waves is 3.04 meters in length, which is almost 10 feet long. Now, I could also ask you how much energy is present in a photon that is being emitted by that wave station and hitting your antenna to provide you with that valuable information and banter. That can be related or quantized by energy is equal to Planck's constant, which we'll get into more at a later time, which is just a number. It's a really small number. It's how many joules. It basically relates the amount of energy versus the frequency of the photon. So we use this equation, and what I could do is ask you how much energy would be possessed by a photon emitted by 98.5. We have the frequency. All we have to do is multiply that by Planck's constant. When you do that out, you would get 6.53 times 10 to the negative 6 joules. So that's how much energy is possessed by that single photon being emitted by that radio station there. Enjoy your day.